So what I'm going to talk about today is getting started in IoT hacking. So this is just going to be a really quick introduction to what you can do to IoT. And the core of this talk is that you don't have to actually buy the devices that you want to attack. Things cost money. Playing with hardware, you break it, but you can do a lot of these things without actually buying the hardware. So I'm going to talk about a device that we looked at. This is a Samsung camera. It's one of these cloud-connected cameras that you're supposed to put either inside or outside your home to keep an eye on things remotely. We bought it off Amazon. It was quite expensive, not cheap. They're not really actually made by Samsung. It's kind of a white label product made by a company called Firmware Recovery. But we got one of these and we had a look at it, and it's got a web interface on it, kind of like you'd expect on a lot of these devices. And it asked for a private key. What it actually meant by a private key was a password. Now, the first time that you went to that page, you obviously hadn't set a password on it, and it wanted you to commission the device to set a new password. So you could log into it, get in as admin, and we could view these requests in Burp Suite going between the browser and the device. Burp Suite is just an intercepting proxy, and we use this a lot in IoT testing. But the first time that you tried entering a password or a private key into that device, what it said is it said that it has no private key installed. Please create a new private key. It's recognized that it's not been commissioned, so we need to do something. So we set a new password. Now, looking at that in Burp, in the background, what's happening is we're sending this data parameter on the left-hand side. The first part of that is check. It's saying, check this password I've sent to see if it's the correct one. And the response we get back from the device is no key. What it's saying is it doesn't have that password set. So we've got to set a password to use it. So the web interface prompts us. It's that typical pattern where you've got to type your password in twice to make sure it's right. In the background, when we set that password, that data parameter, now instead of it being check, is new, set a new password. I've set the password there to BCS IoT 20. So we've set that new password, and we can now log into the device with that password and use it. But how's that all working in the background? How does it know that no password's been set? How does it set that new password? Well, this whole device is based on PHP. It's a PHP-based web server. Now, we had access to the firmware, and I'll show you how we did that in a minute. And we could examine that PHP code. PHP is a scripted language, an interpreted language. So it's written in plain text, or plain text as far as someone who can program would think of plain text. It's not compiled. We don't have to disassemble it. And we can see there at the top in the blue box, it says, if that first bit of page data is check, then follow this path. So we're checking to see if the password's correct. Then in the red box, it says, if the private key that I've got stored in memory is blank, send back no key. So that's the path that's followed when we haven't set a password. However, if we have set a password, it then compares the password we've sent to the password that's stored in memory. You'll notice there's no hashing going on, which does mean the password's stored in plain text, but that's kind of a secondary problem. So this check kind of makes sense. If it hasn't been set, send no key back. If it has been set, check the password's correct. However, then we look at the flow for when we set a new password there. So if that first bit of page data is new, setting that new password in an uncommissioned device. And there we can see it doesn't check to see if a password's been set. It doesn't check to see if the password's correct. So that new parameter, when we send a new password to the device, it will always accept that regardless of a password being set or not. That allows us as an attacker with web access to the device to change the password of the device, even if someone's already set a password. So this is a logical error in how this device works. So with a really simple curl request, a web request there, I can set the password to lol you're hacked. So we've now got access to that device without permission. But how did we see that PHP, and what else can we do with that? Well, you can download the firmware of the device. So it was available on Firmware Recovry's website. Amusingly, when we reported these vulnerabilities in the device, their response was to stop us downloading the firmware from their website. That's just hiding the vulnerabilities. It's not fixing. So we downloaded the firmware for the camera. And as is the case a lot of the time, it's a tar.gzip file, a compressed file. We unpack that and it's got a load of other files in it. One of those is large and of particular interest, work-shnh-model number.wn3. So I run the file utility on that. And all file does is it uses kind of signatures, magic numbers to guess what that file is. And it says it's a D-base file. This is a false positive. It doesn't know what that file is. So at that point, what we tend to do is we turn towards something called binwalk. And what binwalk does is it will examine a compressed file, it will examine a firmware image, and it will look for these magic numbers, these signatures of certain things, file systems, images, and it will try and unpack them for us. So we run binwalk on it, and we can see right at the beginning there, right at the beginning of the file, it recognizes a YAFS file system. YAFS is yet another flash file system. It's a fairly rare file system used on embedded devices. And it will extract that and give us access to the file system from the camera. Now, one of the things I'll do whenever I get the file system and camera is I'll search for words like debug, backdoor, password, roots, and things like this to find interesting stuff on the camera. So I search for debug, and I can see there's three files there. Two of them are debug CGI. They're in the web root of the device. So these are CGI scripts, things that I can call on the device and run. So I've learned they're there. So I go back to the web browser on my camera I have in front of me, and I try running debug CGI, and I just get the response NG. Now I try throwing some random data in it, and it just doesn't do anything. I can't get it to do anything useful. So from a black box perspective, looking at this debug CGI is going to be time consuming, and I'm probably not going to get anything out of it. So what I tend to then do is turn to disassembly. This is a CGI, a compiled CGI file. Now, I use IDA, the interactive disassembly. You can use JIDRA, you can use lots of different tools to look at how compiled binaries work. But we don't have to look at it in too much detail. I'm looking for strings here, and we can see things like gunzip, we can see ls. These are strings that are then being executed on the device. Now, whenever I see a command with the %s in it, that and a call to printf afterwards, that's kind of a red flag for command injection. Being able to put my own string into another command, use a command separator or something like that to run another command. Now, the thing was, this would only allow certain listed commands to be carried out, listed directories, cnetstat and things like that. So with a little bit of reverse engineering and back and forth, we worked out if you called m submenu equals shell and command, and then provided one of these allow listed commands, it would run those commands. So we're now running arbitrary commands on the device. So this is good. This is making progress. And I thought, well, what happens if we put a command separator onto netstat? It wouldn't accept it because it was allow listed. But then you think about ls, list directory. You have to provide an argument to tell it which folder to look at. So I put a slash on the end of it. That gives me a listing of the root directory of the device. So I've got control over more user input. Now what I can do is I can put a semicolon, a command separator, and then who am I? It tells you the running user. And at the bottom there, we've got root. So we've now managed to inject an arbitrary command and run it as root on the device. So this is command injection. We're making progress at attacking this device. Now, the problem is some commands want spaces in them. Here I'm trying to cat etc password. And I put that space in, and the device is escaping that as %20. So I can't get spaces directly into the URL. So this is a problem if I want to do anything more complex. But there's a really convenient way of getting around that. What you can do is you can use curly brackets and commas. It's called brace expansion in Bash. And what it will do is it will take all the things separated by commas and add spaces for you. So now I've outputted etc password. I've got arbitrary command injection as root, so I can do whatever I want on the device. So now we've got the ability to reset the password using the logical floor. We've got the command injection via the debug functionality. We can bring those two together with a script. The command injection is authenticated, but we can authenticate because we can change the password. We bring them together. Quite quickly at the bottom there, all I do is I replace the root password hash with one of my own, and then we can SSH into the device. So now we've got a Linux camera, a little box that's quite powerful that we've taken control of just via the web interface. So this is quite powerful. We took a step back after this and we thought, well, let's look at that shadow password file. And you'll notice there that root does have a password hash. You'll see it's really, really short. It's not a typical MD5, PBKDF, bcrypt password hash we're used to seeing. It's old school descrypt. Now, the thing is, this limits the password to 8 characters long, and it's very, very quick to brute force. What that means is we can do an exhaustive brute force search for reasonable symbols and English characters. We wouldn't normally do this if it was a longer hash, and that gave us the password. This is the password for all of the cameras, which works over SSH. So we can connect into the device and do what we want. So from the firmware of one device, we've learned about several vulnerabilities as well as a password that will allow us to attack all of them. You might have seen the same. Physical access means game over. And people, when they say that, they really mean servers and laptops. That idea that if you've got prolonged physical access to a device, you can attack it and you can get data off it. Now, the problem with hardware and IoT is the device is already in the hands of the attacker. We can go and buy them off Amazon. We can go and buy them from Currys, PC World, Argos, wherever. Get hold of these devices and attack them. But the thing is, we don't even really need to do that. We can skip all of these steps and just analyze the firmware. When we look at a device, an embedded device, they're kind of similar to computers around us. We've got the processor, which is the processor, generally ARM or MIPS or something like that. We've got the flash memory, which is the non-volatile storage, like the hard drive that stores the firmware. You've got the RAM, the volatile storage. They're pretty simple and very similar to devices around us. Why do we want that firmware? Well, if we take a typical IoT device that's got Wi-Fi, a user interface, USB, and so on, if we analyze that as a closed black box, we can't really make progress on understanding how it works. But if we expand it out, break it out and examine the firmware, we can access inner components of it and really deeply understand it. So we've got the flash, the firmware, we can read the firmware, we can modify the firmware, we can find shared keys and passwords like the one on the Samsung camera. We can gain access via a serial console to a running device, one that we actually have, to inspect things and how they operate. The RAM will contain secret keys and decrypted data in it. And we can use JTAG to access all of those different components. But what we're really looking for here is we don't want to get something off a device that's in front of us that only impacts the device in front of us. We want to get something off the device here that impacts many or all of the devices. We tend to call these break once, run everywhere attacks. So that's the idea that you break one device, you find a vulnerability, a shared password, a shared key off one device, and it impacts lots of them. That shared password across all those Samsung cameras is a key example of that. So how do we get hold of the firmware? Well, there's lots of different ways, and in kind of order of increasing effort, at the top level there is downloading it. Just download it off the website. It's really, really common to find that you can just Google, especially for things like cameras and DVRs, and you get hold of the firmware like that. You can also intercept it. A lot of devices will update their firmware from a server. It's still very common to find that's not properly encrypted, so you can just intercept that and get hold of it. There are other ways. A serial console or telnet onto a device will let us recover the firmware. We can do what's called a chip-on memory read. So all of these flash chips, things like SPI flash, NAND flash, we can read those either when they're on the device or off the device, chip on or chip off, to be able to read that firmware. There's also JTAG and more advanced attacks, but we're going to focus on downloading because it's really easy. You don't have to own the device. A problem, though, is that quite often those updates aren't complete. Sometimes the update will be everything, the bootloader, the operating system, and the application. It's becoming increasingly common to find that it's just the application. It keeps the updates smaller. It means it's less likely to completely break the device. But nowadays, as things are getting bigger and bigger, we're finding that you get Delta updates, which is just the component of the application or binaries that run on it. So sometimes when you download the firmware, intercept it, you don't get everything you need. Now, going back to that firmware we got for the camera, this one, you can still download it off the internet if you know the URL. It's just a tar.gzip file, so we can extract it. We then tend to use the utility file to see what that file is. With that work one, it doesn't know what it is. Here it says it's data. It's tried guessing and it didn't get it right. If we try it on another file within there, we're trying on that U-image one, you can see it says it's a U-boot legacy U-image. It's guessed what that file is. It's Linux 2.6 kernel, so it's old. It's ARM, so it knows it's ARM. It's given us some information about the device. So file does sometimes get things right. Another thing we can do is use hexdump. Hexdump is just a simple command line utility that shows us the hex and the corresponding ASCII strings for that. So we can see the structure, the strings there. We can tell it's not compressed, it's not encrypted. We've got something good to go from there. The other tool, binwalk. Binwalk will look at that image and look for these magic numbers or signatures. So we found that YAFS file system in there. It's really important if you put binwalk onto a machine, do not use the one that comes with Cayla. The one in Cayla, it's missing several of the dependencies that means it won't work on firmware images. So go to GitHub, get your own copy of it, and get looking at firmware images. Now, once we've extracted it with binwalk, we can just browse it like any file system. So we're looking in an app directory here. We've got lots of shell scripts. We've got some WAV files that play noise and stuff like that. Shell scripts.sh are great because we can understand them just by opening them in a text editor. There's none of this disassembly or messing about. Now, what we've done with the firmware image since we've extracted it is static analysis. We've just tried looking at the files. We haven't actually tried running them. But you can also do dynamic analysis. So static analysis is analyzing it without running it, whereas dynamic, you actually run the code. Static's quite good because you can look at the entire application, whereas dynamic, you might only examine the paths where the code actually runs. There can be things that are uncovered. That does mean that static analysis can find hidden functionality. That debug CGI and how that works, we probably wouldn't have found that just purely by dynamic analysis. Dynamic analysis can be really fast though. You run the binary, if it does something interesting or good, it's done it. But a problem with static analysis is you're inferring what happens. You haven't actually demonstrated that it happens. So we prefer a combination of the two, static and dynamic analysis, to see what happens. Now, looking at this device in a little bit more depth, this Samsung camera, I found there was two directories. Both with very long random names, FHZ, JF, blah, 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 XPZ. And then within there was another executable file, DMP, QT, blah, blah. Now, those long random files to me suggest that someone wants to hide them. They don't want people to see them. So we run file on that binary, and we can see there it's an ARM executable. That's great. That's kind of what we're expecting. Dynamically linked, so it imports binary libraries from somewhere else. But at the end there, you can see importantly, it's not being stripped. Stripping's taking out the symbol names and function names from the binary. Now, if they're left in, it makes reverse engineering much easier because the functions have got their natural names. Another tool we quite often use is strings. All strings does is look at a file and extract ASCII strings over a certain length. And you can see when I run it against this binary, there's HTML in there. It's probably generating a web page, but this can find things like passwords, API endpoints, server names, private keys, everything. It's a very good way of doing a quick pass. Now, in terms of reverse engineering, I said earlier, shell scripts are the easiest way. They're just opening them in a text editor. Same with Python and PHP. Some languages like Java and C#, you can turn back into human readable code quite easily. But when you move on to C and C++, you've got to disassemble them or decompile them to understand what's going on. So it gets more and more difficult. Now, unfortunately, this is C, this particular binary, so we have to open it in IDA. So we open it in IDA, and because it's left the symbols in, we've got the names of all of the functions. We've got set web service mode, initialize message, append data. That will tell us what a function does without us actually having to reverse engineer it. But there's still a lot of inference. We still have to guess what's going on. We've got calls to functions. Lots of stuff there isn't particularly obvious. but any strings that are left within a firmware are very, very useful. Now we can see a lot of calls here to getenv, which is get the environment variables from the Linux system. And I look here and we can see that we're getting the environment variable remote_ADDR, the remote address. I don't have to really do any more reverse engineering here. I can see what's going on. Now I want to do dynamic analysis. I actually want to run this binary to see what's going on, but I don't want to do it on the device. I'd rather just run it on my laptop if possible. So we use something called QEMU, the emulator that can emulate ARM and MIPS and so on, to run an ARM binary on our Intel laptop. So I tried running this weirdly named binary, and you can see that when I do that, it gives me a 404 not found, comes back as HTML, but at the bottom there it says change web service mode -1. I'm not sure what that means. I jump back to the code and we can see it's getting that environment variable query string. And then after that, it's looking for service, the word service. Now, I could reverse engineer exactly what this does. Well, now that I've got the ability to run the code, I can do some dynamic analysis of it and see what it's actually doing. So I set query string equal to service equals 1. So it's just a guess. I'm just having a stab at this. There's no penalty to me getting it wrong. So I set service equals 1, and you can see now at the bottom in the red box, it says change web service mode 2,1. So we've changed the response. It's taken that and it's passed it and done something with it. What it's actually doing is it's turning off and on that big web interface we saw earlier on. The camera can be put into a limited mode where that web interface doesn't really do anything. Now, whenever there's user input sent through to something like this, we start thinking about buffer overflows, sending long bits of data to see what happens. So what I do is I send a string of A's. I send 1,243 of them. There's a reason for that number, but it doesn't really matter why. So you can see there at the top in the green box, I'm sending lots and lots of A's. And then at the bottom in the red box, we can see we've got segmentation fault. We've caused a buffer overflow. So now the binary is doing something unexpected. But can we do something bad with this? Well, with QEMU, one of the things we can do is enable GDB. So GDB is the new debugger. It lets us examine registers, the program counter, and things like that. So I start that up and I connect to it. I can then trigger our buffer overflow by sending that long string of A's. And you can see there, the program counter turns to 41, 41, 41. It's got those letter A's in it. 41 is the ASCII of A. So we've got control over the program counter. We can cause that binary to jump into any part of memory on the device. Now, how do we know how far through that buffer that those A's were? Was it right at the beginning, right at the end? There's a really useful tool called pattern create and pattern offset. What they do is they create an incrementing string. And instead of sending all A's, we can send this incrementing string. We can then see what the program counter is, and we can work out how far through that string the program counter has come from. So we create one that's 1,200 long. We dump it into the device. And you can see there, we get the program counter 316A4230. I put that back into the tool, and it tells us that it's 1,052 bytes into that buffer. So we've got 1,052 bytes before we've got control over the program counter. It's quite a lot of space, plenty enough space for us to put code in. So I test that. I send 1,052 A's, and then I set the value to BCDE, so 42, 43, 44, 45. I send that through to the device, and you can see I've changed the program counter to BCDE. So we confirmed it's 1,052 into that buffer. Now, the next thing, we want to actually execute code, so the device does something we want. We've got 1,052 bytes to play with there. So what I do is I write some really simple shell code. This is the simplest shell code you can write. It's literally a C program that runs the shell. That's it. System bin sh runs that. We turn that into assembly on the right-hand side there. And from that, we can then inject that into the buffer and run it. So the attack looks like this. We've got a load of A's in yellow, the padding. We then have our payload. the red, and then after that, we have another little bit of padding in purple, followed by our pointer that jumps back to the beginning of that red bit, the payload. So what should happen is we'll change the program counter to the beginning of our payload and run that. So that's what it looks like when we send it. We've got load of padding, our shell code, and then in red, that program counter that we want to send. That should jump back in there and execute that code. And as expected, once we've done that, we send that request through to the device and we've got a shell. So rather than it changing the web service of the device, we've now got the ability to run commands as root through the web interface of this camera. So we found that vulnerability and we exploited that vulnerability and we developed that just running it on a laptop. We didn't have to have the camera next to us, which is a really, really good way of doing these things. This combination of using static and dynamic analysis is absolutely vital in finding vulnerabilities in internet connected devices. Get hold of the firmware, do static analysis to find interesting things, do some dynamic analysis to make sure that they might be possible. Keep on going round this loop, trying different things, gradually chipping away at the problem until you manage to exploit things. So the general methodology is getting hold of that firmware, download it, extract it from a device, get it from the mobile app sometimes, unpack that firmware, start exploring it and find those vulnerabilities. I think if you go back through this talk and you look at those tools I used and the things I did there, it's a really powerful technique and a great way to find vulnerabilities. A lot of low-hanging fruit still out there in the world of IoT. Anyway, thanks for listening. I hope you enjoyed that. I hope someone learned something from that, and I hope some people will go away and have some fun trying some of those things. And as Adrian said, I'm CyberGibbons on Twitter. Follow me if you like bananas, bikes, and hacking the IoT.